Hi everyone, my name is Nanya. I'm glad to introduce our work A, adapting image models for efficient video action recognition. We've seen that VIT has achieved great success in different computer vision tasks. And recently, based on VIT, there have been more and more image foundation models being proposed, and they have demonstrated excellent transfer learning performance on different downstream tasks. In video action recognition, the common paradigm is pre-training then fine-tuning. That is, we first pre-train the image model on image data, and then inflate it into video models, and then train the video model on video data. But there are some drawbacks of this learning paradigm. The first one is large training cost. This is because the video models are usually very large, especially if we want to inflate from image foundation models. The second one is catastrophic forgetting. That is, we may lose some good properties in the pre-trained image foundation models if we full fine-tune the video model on video data. So to alleviate these drawbacks, a research field called parameter efficient fine-tuning has been proposed. In parameter efficient fine-tuning, researchers keep the pre-trained models frozen and just add some prompts or dampers into the frozen model to tune the features. But in previous works, all the works are doing the same modality adaptation, that is image to image or language to language. But here we are doing cross-modality adaptation, that is image to video. So video modeling can be split into spatial modeling and temporal modeling. To achieve good spatial modeling, we can simply add the adapter into the pre-trained image model to tune the spatial features, and this can already achieve good spatial modeling. The challenge is that how to introduce effective temporal modeling. Our strategy is very simple. We simply reshape the input tensor and then reuse the image pre-trained self-attention layer, but apply it on the temporal dimension of the input to learn the temporal information from different frames. And then we add a damper after the self-attention layer to tune the temporal features. So this simple strategy achieves pretty good temporal modeling without introducing new temporal layers. And finally, we add another adapter to tune the spatial temporal features jointly for better performance. And here is an emulation study to show the effectiveness of different components. We first introduce three baselines. The first one is a frozen space-only baseline. That is, we only tune the classifier of the image model. We can see the performance is very low, but the tunable parameters is also very few. And the second baseline is a full fine-tuned image model. Then we can see the performance is increased, but also the tunable parameters is largely increased. And the third baseline is a full fine-tuned video model. And we can see the performance is further improved, but also with a large increase of the model parameters. So in our method, we first add the spatial adaptation to the frozen image-only baseline. Then we can see we can match the performance of the full fine-tuned space-only baseline. That means spatial adaptation helps the model to achieve good spatial modeling, but we are using much smaller number of tunable parameters. And when we add the temporal adaptation, the performance is further improved, which even outperforms the performance of the full fine-tuned video model. But we are using much smaller number of tunable parameters. And finally, when we add the joint adaptation, the performance can be further improved. So these results show how our method gradually adapts a frozen space-only model into a video model. And also when we switch from the ImageNet pre-trained model to GLIP pre-trained model, the performance can be further improved. This shows that our method can benefit from stronger image foundation models in the future. Here we show the comparison with state-of-the-art methods on Kinetics 400. We can see that our method achieves better performance than previous works with much smaller number of tunable parameters. And similarly, on Kinetics 700 and Diving 48, our method achieves competitive or better performance than previous methods using much smaller number of tunable parameters. And here we show that our method can be applied to different pre-trained models, such as VIT or swing transformer. And also we can largely save the training cost compared to fully fine-tuned video models. And here we show that our method also has the benefit of data efficiency. That is, when the labeled training data is limited, we can achieve larger improvements over the full fine-tuning baseline. Our codes and models have been released. Thanks for your interest.